Okay. So today I will tell you about machine learning for our topic, natural language processing. And yeah, machine learning is used a lot in a lot of the papers that you will read. So that's why I want to give you some basic introduction to the topic so that you know what you will read about and algorithms you'll read about. Yeah, and the outline of this presentation is I will start with a very, very informal definition of what machine learning is, and I will provide some example to make it more concrete. I will then show 4 machine learning algorithms. I think it's 5, but 4 or 5. And I will always show you like the motivation and the main idea for each algorithm. And I will illustrate it with an example. I will show how do they learn or how do they train and how do they classify, how do they work. And I will show you how much are they used or what are they usually used for and what are their assumptions. You know, each of these algorithms, they will have some assumption. I will explain what that means. And so you know when can you use the algorithm, when should you not use it. And also interpretation. All of them learn something, and in the end you should also maybe be able to interpret what has my algorithm actually learned, so that you can learn something about the data you serve. In the end I will go also a bit into what kind of types of machine learning there are, because we will mostly cover one type now. And finally I will tell you what can you do when you want to improve your whole machine learning system. That's going to be the final step. And it's fine if you don't understand one of the words there now, because they will all be explained step by step when I go through. I think it will take about 50-60 minutes in total. It will be a bit longer. Yeah. So a very informal definition of what machine learning means is it means that a program gets better by automatically learning from data. So you have some program that does something, it gets more data, and its performance improves somehow. Yeah, and somehow I will explain to you how it does that. So that's a very informal definition, and we'll see what it means by looking at one concrete example right now. So my concrete example is of course geared to our topic, natural language processing. So I will talk about named entity recognition, or I'll talk about something a bit more simple. We want to recognize mentions of persons in a text. So for example, here we have 3 sentences. Angela Merkel made a decision, Tiger Woods played golf, and Tiger ran into the woods. Maybe like a news headline, Tiger ran into the woods somewhere. So what we want to do is we want to know that Angela Merkel is a person, Tiger Woods is a person, but Tiger ran into the woods, there's just an animal and a forest and no person. So what could you do? First idea, maybe you could use some handwritten rules. Like you see that woods, for example, in the last sentence it's written small, so maybe person names are always big, but that's not enough, and then you could think of more and more rules and their interactions and write all of this by hand. But it might take a lot of time to think of all the rules and to be sure how they exactly interact. So another idea would be to say, okay, we could learn all of these rules. How can we know that this is a person and this is not a person? That Tiger Woods is a person, but Tiger ran into the woods, that there is no person. How can we learn the rule for that? And that's what I will try to show you in this seminar. How can we do that? So the first thing that we have to do is we have to create features. What does it mean? For the machine to learn if a word is a name, you have to tell him what to look for in the word. So concretely, you have to define attributes or so-called features that might indicate a name. What can this be? The word itself, like Michael would probably always be a name, for example. If the word is like some object, like I call it a known noun, like hammer or boat or tiger, this might indicate that it's not a name. It's of course not always that way. Tiger, we know, can also be a name, but it's more probable that it's not a name. And if the word is written with a capital letter or not, the part of speech, if it's a verb, then it cannot be a name if it's a verb in the sentence. So these might all be features. You might think of more features, other features, that could tell this algorithm, okay, if this happens, maybe it's a person. And these features will not be learned automatically. You have to design them yourself. You have to tell yourself, okay, please look at the word itself, please look if it's a known noun, please look if it's capitalized. However, your algorithm will learn what are typical features. What is typical for a person? Like yeah, Michael may be typical for a person, Ahmed, Ina, these might all be person names that might be typical, and the algorithm could learn that automatically. And maybe it's typical for a person name not to be a known noun, like the three above are all, I think they don't have another meaning in the English language. The word that is capitalized, it's more likely then that it's a person. Usually they will be written big. And it should have the part of speech proper noun. I will not go into too much detail what proper noun is because I don't know it myself, but you just have to know that, yeah, you can have verbs and proper nouns and adjectives and so on, and persons will probably not be adjectives or verbs. Yeah? But the machine should learn these typical values automatically and also combine these values. Okay, if I have something that's tiger and it's capitalized, probably it's a person. These kind of combinations should learn automatically. So what do? You start by creating some training set. You create a set where you have sentences and there are words that are person names and there are words that are not person names. And you might end up with a table like this. So you have, here's our first sentence was Tiger Woods played golf. So we have the tiger, it's a known noun, it's written with a capital letter. In this sentence it's a proper noun, and yes, it's part of a name. Woods is the same basically, but for example, in the last sentence, Tiger ran into the woods. There, woods, it's not written capital, it's a plural noun, that's the part of speech, and it's not a name. So we create this kind of set where we already pre-classified whether it's a part of a name or not, and we give this to our machine learning algorithm. Okay, now I will show you one specific algorithm, which is naive Bayes, and how it trains. Yeah, how does it learn? What it does, it basically counts. So for each feature value may be it's capital or it's not capital. Feature value can be the word Tiger or Michael or Ina. And for each of these feature values, naive Bayes will count how frequently does this feature value occur in person names, and will also do the same for other words. So one example, if you want to know if a capital letter indicates a name, you'll just count how many of the person names you have are written with a capital letter and how many person names do you have in total. And then you get something like 80% of the person names are written with a capital letter at the start. So this tells you, for example, how likely is a random person name. So if you take any random person name, how likely is it that it's written with a capital letter? Now you might think, okay, how can it be that a person name is not capitalized? It's always. But there can be noisy text, like I took some tweet here, some real tweet. Somebody writes that Tiger Woods' smile is hilarious. And she writes Tiger Woods small. Yeah? So you can have noisy text where you cannot simply take this as a rule. If it's a name, then it must be capital. So we will get some value between 0 and 1. What you also do is you also count the total frequency of classes. So you count how frequent are person names in general. How many of words are parts of person names and how many are not. So you end up with something like 50% of, 50 probably not, more like 5%, maybe 5% of all the words are person names or something. Then when you've done this training, you also do it for the other class. You do the same for the class that is not a person. Yeah? So you count also how many words that are not persons are capitalized and so on. That's already finished. So this is a very simple training algorithm. It just counts. And now let's see how it classifies. Let's try to classify actually the word tiger in this sentence. Tiger Woods played golf. So we know it's a person. So let's see if it will achieve this result as well. And we assume that 5% of our words are parts of person names. So this probability of a person name is 5%. And we also assume that we train these probabilities. So we know, for example, 1% of all our person names are Tiger. Yeah, the other maybe Michael, Ina, whatever. And 85% are written with a capital letter. 80% have proper noun as their part of speech text. And 10% are known nouns. So like Tiger is also a noun. And we also have these values, as I said. We also train them for the others. We also counted those. And then we get, of course, different values. Okay, this one here I now said is the same. Okay, also 1% of the words are tiger, maybe a bit high. Okay, and 5% of the words are written with a capital letter, of those that are not person names, and so on. So we get these kind of values. And now, if we want to classify this word here, we see that it is tiger. It is written capital. It is a proper noun, and it is a known noun. So we can multiply all of these probabilities now. And then we get this result. We get 0.01 times 0.85 times 0.8 and so on. And we multiply with these 5% at the end. That's the total chance that any random word is a name. And then we get this value. When we do the same for the other class, we multiply these values and we multiply it with 95% at the end. And we get this value. And you see that this top value here, it's bigger. Yeah, it has 1 0 less. And that means that we will classify this as a name because it's more likely that the random word is both the word tiger and it's a name than the chance that we get that the random word is both tiger and it's not a name. That's why we would classify it as tiger. So that's already the classification. I will also give you an overview now. And by the way, if you ever have any question now, just ask it directly because it will be more easy for me if I answer it directly rather than at the end when maybe you've lost me somewhere in between. Okay. So now just an overview. This is the same what we did in this example. When we want to classify some word, we just multiply the feature value probabilities. So these feature value probabilities would be what's the chance that a person name is capitalized and so on. And then we look if it's capitalized, then we multiply with this. Otherwise, we would multiply with 1 minus this. So if we get some non-capitalized person name, for example, and we take these values, then we'd have to multiply with 0.15. Yeah? Okay, so we make all these multiplications. We multiply also this total frequencies, was this 5% and 95%. And then the higher score wins. That's what we just did. So now you already saw one algorithm. It's quite a simple one. Here again is the overview. I guess I don't have to go into too much detail for all the classes. You count all of these probabilities. You count the total probability. You compute this class score by multiplying, and then you take the highest score. So that's just an overview. You can look at it later also. Yeah, so that's the first algorithm, the naive Bayes algorithm. And does anybody know already what kind of assumption this algorithm makes?
Independence of
yeah.
random variables involved.
Independence of what?
The random variables involved.
Yes, kind of. There is an independence. And what kind of independence?
Conditional independence.
Yes. So to go, yeah, I put it this way. The naive Bayes assumes that one feature is independent of another feature when we already know the class. What does it mean? It would mean that when we know that this word that we have, like tiger and tiger woods, is part of a person name, the probability, for example, of the feature, is it capital or not, is independent of the probability that the word is a known noun. Yeah, so these are two features, and when we say when we already know it's a person, then these are independent. And that's not completely true. Let's take one very strong example. We also had the feature that the word itself. Yeah, and if the word is tiger, we already know it's a known noun. Naive Bayes, however, would think that if it's a person, then the chance that it's tiger and the chance that it's known noun are independent. So it would say, okay, we have a person, it's tiger, the chance that it's a known noun is 10%. But actually it's 1 because it is always a known noun. So this assumption is not always true. That's why it's called naive Bayes, because it has this assumption. However, the naive Bayes often classifies well even if the assumption is violated. So even if it's not true, if it's not violated too strong, it will often classify well. Yeah. Now when you have classified and everything, you still want to know how good is my algorithm? How well did I learn my classification? And you do this by evaluating your performance on a test set usually. So that means you use some set that you didn't use in training. You didn't learn on it, you didn't use it for learning. And you could look at, for example, how many words did I classify correctly. However, if you just take this correct classification rate, it can be very misleading. For example, let's say our classifier simply always says it's not a person, always. Then if we only have 5% person name words, we get a classification rate, correct classification rate of 95%. So this rate by itself, it can be very misleading. And there are other more informative measures. For example, we can look at so-called true positives and false positives. These are the words that are correctly classified as persons. So the classifier says it's a person and it is a person. That's true positive, or incorrectly classified as person. That would be classifier says it's a person but it's not. That's false positive. And also the same for others. There would be true negatives and false negatives. If it says it's not a person, but it actually is a person, that's a false negative, for example. And if you look at these four measures together, they will tell you a bit more than just the classification rate. Now what you have to keep in mind is that the best performance may be subjective. So it can be, for example, you want to capture all the persons occurring in the text, even if you capture some words as persons that are actually just random words. Let's say you want to capture all the persons that are mentioned in connection with some crime. You just want to have all the names, and if you have some random names that are not actually persons, you will care about that later. This would be a different kind of goal than saying you only want to capture words that are definitely persons. For example, if you want to build some reliable list of people that are very much talked about, but you want to be sure they're only persons and not like things that are talked about, then you want to, you have a very different goal. And that's what you have to keep in mind when you evaluate your performance, that you know what do you actually want from your overall system. Yeah, okay. Hope that's understandable. Now, I said also I will always talk a little bit about interpretation, and I will just talk about the interpretation of what naive Bayes learned. And basically it's fairly straightforward. We have these feature value probabilities, and we can compare them for the different classes. So if we see that one feature value probability is much higher for the one class than for the other, well, this simply tells you this feature value more likely indicates the first class than the second. So for example, if the chance that a name is written with a capital letter at the start is 85%, and for other words it's just 5%, then capitalized words are more likely to be parts of person names. That's basically how you could interpret naive Bayes. And one good thing about this naive Bayes is, because it makes this assumption of independence, you can look at each feature independently. So you can really look at each feature and see, okay, does this mean class 1 more or class 2? And you can check if your algorithm if the results look plausible, for example. Yeah, I made some overview here. Here with these nice dolphins and orts and stuff. Because I want to give you one complete overview. Basically, if you just take this overview from this seminar, that's fine. If that's all you remember, then I think that's already good. Because it will show you what happens in a machine learning system. You start always with some data acquisition. So you have to first get some data. No, you first have to get text, for example, where you have the person names already pre-classified and so on. And there it's important to get data similar to the data you will classify. If you think you have some English text and later you use your classifier on German text, it will probably not work. And also more subtle things, like you classify it maybe on reports about sports persons, and later you want to try it on politicians. Maybe there's some difference and it will not work as well as you thought. The next step is you need to represent your data as features. So that's what you saw already. We derived these features, capital and so on. And there it's important that you have to keep the information in the features that will allow your learning algorithm to classify correctly. So for example, let's say capital, it's a very good feature for classification of person names, but you don't have that feature. Then of course your algorithm cannot use this feature, and no matter how good your algorithm is, it will not be as good as when you put this feature in. Yeah, so that's also a really, really important part that you have to keep in mind. No matter how good your algorithm is, if your features are not carrying the information you need to learn, then it will not work well. So yeah, then comes the machine learning algorithm, or the training of the machine learning algorithm. There it's important that you know what kind of assumptions does your algorithm make, and do they fit your data well enough. I already told you they don't have to be perfect. Like naive Bayes assumption is usually violated and it still classifies well, but if it's violated very strongly, its performance will go down. So that's what you have to care about. And finally, get your performance evaluation. There it's important to know what measure of quality you're interested in. I just talked about that. And yeah, that's why I also made here, there are the dolphins, they are the machine learning algorithm, and they have the performance evaluation. So they might have different things that they look for. Yeah, this kind of thing will optimize something, but these owls, the performance evaluation really has to check whether what you're really interested in, whether you really get that, whether you really get all the names when you want all the names, or whether you really get just correct names if you want just correct names. Yeah. Okay. Now we'll go through 4 more algorithms.
Robin?
Yeah.
Can you go back to the Tiger Woods example slide from the page?
Yeah. Which one?
The example probability.
Example, you mean? This one? Yeah.
So why, this is the probability that you see tiger and then it's a name.
Yes.
So why don't you compute the probability that it's a name under the condition that I see tiger?
Okay, I mean, yeah, I could tell that. I mean, basically, if you just want to classify, if you just want to say, is it a name or is it more probable that it's a name or is it more probable that it's not a name, then all you need are these scores, because you can tell if this score is higher, then it's more probable that it's a name. If you are interested in the exact probability, so you see here, I mean, these are both very low, and that cannot be. It has to be a name or something else. If you're interested in the exact probability, or that at least that one that naive Bayes predicts, then you have to normalize. So you'd have to, these two would have to add up to 1. But that's basically, I left this step out because it's quite long, presentation. I thought, okay, for just classifying it's not important, but yeah, if you want to get some measure of, for example, how confident is your prediction, then you have to normalize these values by making sure they add up to 1. Yeah.
So you are saying if you just want to know which one is larger, it's identical. But these probabilities are conditional
You
one,
would
right?
just divide both by the
Sum.
probability of just seeing tiger, then you take the conditional probability, right? And you divide by the same value, so it's...
What do you mean? So.
If you want the probability that you see name, given you have seen tiger, in this example, you would just divide by the probability of seeing tiger alone. And you do the same for both probabilities. So
yes, but I mean, what I meant is mathematically. I think in this case, what you can simply do is that you just. I think that you can just divide both by the sum of these, no? Then you get the normalization.
Yeah.
Like you don't have to. I mean, that's basically the same. That's equivalent to what you are saying, because the sum of this should be 1.
Probability
Yes.
of tiger, yeah.
Probability of tiger. Yeah.
Yeah, the sum of 2 is probability
Yeah.
of tiger.
Yeah, and if you assume, of course, that you have a tiger, like if you say, okay, I take the probability that it's named given that it's a tiger, then it's fine. You can just add the sum, divide by it, and yeah. So this is all the same. Yeah. And you get the probability. Okay. More question. Yeah. Okay, I'll go through. I have this. Okay, so here's where I was. Okay, so that was my overview over the whole system. And now we get to a bit similar algorithm, and I will first show you the motivation for this. I already told you that this assumption that naive Bayes makes, it's not correct often. Yeah, and in some cases it might actually disturb our classification. For example, I told you tiger is always a known noun. Now let's just assume that those features indicate that it's not a noun. Let's assume that for now. Let's say tiger usually is not a name, and a known noun usually is also not a name. In this case, naive Bayes ignores that if you have a tiger, you already know it's a known noun, and therefore it will underestimate the chance of tiger being a name. It will overestimate the chance of tiger not being a name. And yeah, if you have a lot of, for example, if you have a lot of very strongly correlated features by accident or for whatever reason, then naive Bayes performance will go down. And yeah, now what can you do about it? One idea would be you say, okay, I don't look at each feature independently, but I look at them together. So I look at some kind of combination, and that might help. And that's the motivation I would give for logistic regression. And the idea, yeah, you learn the weights together, not separately. And what you have to do, you have to first make all the features numerical. You have to make them all into numbers for this algorithm to work. So example, if you had before, you had these categories, part of speech, it's a verb or a noun or this or that. And now you make one feature for each category. So one feature for verb, it's 1 if it's a verb, it's 0 if it's not a verb. You make one feature for noun, 1 if it's a noun, 0 if it's not a noun, and so on. Then you have just numbers, and now you can combine them by making a sum. So you could make a sum of all the feature values times some weights that you have to learn, which are similar to these probability values. Yeah, and you have to learn them. And now the sum should be very high, that's the idea of logistic regression. They should be very high for person names, and they should be very small for non-person names, so that you can differentiate between them. Yeah, and the weights will indicate how strongly a feature value indicates a person name. And because you learn them together, these correlated features will not harm your classification as much. Yes. Now we'll just show you some sketch, yeah?
Doesn't this also assume independence much the way Bayes does? Because the weights are per feature, as opposed to like conditioned on a feature's value or something like that?
No, it does not assume independence in the same way, because I will show you how you will train it later. But because you make some relation of the whole features, of the whole feature sum, which is feature times weights plus feature times weights to the output, because of this, when you have correlated features, their weights are not able to both rise in the same way. They will be put down a little bit. Yeah, so it does not assume conditional independence like naive Bayes does. I don't know if that satisfies you. No. Okay, I mean, I'm how to say, I will not go into very deep detail into most of these algorithms because, we have to cover, or I want to cover 4 more or 3 more, and I just wanted to give you the knowledge how to use them and so on. That's why I don't have always all the details now for the mathematical background and so on, but basically this logistic regression does not assume conditional independence. Yeah? So it does not assume that if you know it's a person that 2 features are independent of each other. Maybe it will be more clear because I'll make one example about it. First I made a sketch here. Here you have your feature values. So this might be it's capital 1 or it's not capital, then it's 0 here. Here it's maybe, if it's a verb, it's 1 or whatever. So these are your feature values, all are numbers now. And here are your weights, the ones that you have to learn. And we have also one term here, which is without a feature, and this has different names, sometimes bias term, intercept term. What it means basically is, or what you can get from it is, well, it may be that in general the chance of having a person name, independent of all the other features, is lower than having another word. So this is what this would tell you. For example, if this is very low, it will mean the chance of getting to 1 is just lower in general. Yeah? Now this sum here, it will give you some value between minus infinity and plus infinity. And what you want in the end is some kind of probability. Yeah? You want some probability that you have a person, for example. So what you do is you transform this value, which is between minus infinity and plus infinity, to something between 0 and 1. And what you use for this is this logistic function. And now, without going into too much detail, of course, this function is not completely random. Like, you could use other functions. You don't necessarily have to use this function, then it wouldn't be logistic regression, but you could use other functions. But this function has some nice properties, which you can maybe see here. You see that around the point where the class changes, from here to here, the class changes. Here it's 1, or here it's 1, here it's 0. Around this time, around this class boundary, it rises very sharply, and here it rises less sharply. So this has the effect that it will separate well. It will separate the positive examples from the negative examples, because if you think about the difference to the correct answer, which for correct examples, for true training examples, it should be 1. Yeah. Now, if you have some high value and you have some very high value, the difference will not be very big. So the algorithm will not care so much if you have 6 or 6,000. However, if you are very close here, the algorithm will be very quickly becoming more and more incorrect. Yeah? If you have here 0, 1, and you are just here, and if you have -1, you are already here. And this will try to prevent that you have a lot of data that is very close, which classification is very close to this boundary, and will really try to get you more to 1 and 0. Like there are more background to this. Why is it this function? If you want, then I can go into it after I'm finished a little bit, because I have some slides that I took out if you want to know why it's this function. But yeah, or why this function, let's say why this function is plausible. But for now, I think it's just important to know, okay, it will really work well if you want to classify something between 1 and 0, and you will get some probability in the end, and it will try to separate really well into 1 and 0. Okay. So yeah, let's look at our running example, which is Tiger Woods played golf. And assume now training is finished. Assume we learn these weights. Assume that known noun, has a weight of -1, tiger, it has a weight of 3, proper noun has a weight of -0.5, and our intercept term has a weight of -2. So in our case, these values would indicate that actually tiger usually is a person. I mean, it's a bit made up example. And known noun usually indicates it's probably not a person, and so on. Now what you do is you just multiply again. In our case, all of the features have the value 1, because tiger, yeah, this is a tiger. Known noun, yes, it is a known noun. Proper noun, yes, it is a proper noun. So all of the values here are 1. These are these. And then you multiply them with the weight. So you have 1 times -1, 1 times 3, 1 times -0.5, and you subtract this bias term, which here means probably most of the words are not persons. And then you get 0.5 at the end. And if you plug it into this function, this logistic function, you get 0.62. And now you can interpret, okay, first it looks more like a name because it's above 0.5. And you can interpret this as a 62% probability that it's a name. So, yeah, so it's not very confident, but it's more likely to be a name according to these values.
Is the value, you should always interpret it as a probability because it's negative.
Huh?
It can be negative, the output of this function.
No, it cannot be. Here it can be negative, but when you plug it into this function, this transforms it to a value between 0 and 1. So it can never be negative this year. Yeah. Yeah, and also like under certain assumptions, you can actually show that if this certain assumptions hold, this will give you the probability actually. So yeah, it's not just some value between 0 and 1. Yeah, now training, how do you do it? Basically, you have some equation system. Yeah, you have these values should give 0 when you give them into the logistic function. This kind of value should give 1 when you give it into the logistic function, and so on. So you have, for each training example, you would have one of these equations. So you have a big system of equations, and the bad news is that something like the best fit, so here you want a 1, here you rather want a 0, cannot be computed analytically or directly. So you have to use iterative procedures. Yeah, and as I said, it's not our topic here, like it goes way too much, I think, into detail what they exactly do. But, yeah, you just have to know that you have to run some algorithm which runs several iterations. Will not just run and give you one result, but will run and try to get closer to the result, try to converge. Yeah, and you have to know that the weights are estimated together. Yeah, so here you will always try, you have the full vector with all your features, and then you try to make the weights so that this is 0 and this is 1 and so on. So you don't estimate them independently. And yeah, the interpretation is similar to naive Bayes. If you have some high weights, that means that the probability of yes or of 1 is increased by the corresponding feature. But you have to interpret the weights together. So for example, let's take a very, I think, clear example. Let's say we have some feature which says this word is preceded by a doctor, by Dr. dot. Yeah, and then usually you would think, okay, Dr. Smith, it will probably afterwards be a name. And let's say we have another feature, second feature, which says that before there's a professor doctor. Again, probably it will be a name then. But let's say for some reason in our text, there are only professor doctors. Like doctors, they all died, I don't know. We only have professors. So actually what happens now is that both features will always have the same value. There will always be 1 if there is a professor doctor before, or there will be 0 if there is no professor doctor before. Now basically we have duplicated our feature. And now what happens in logistic regression, if you have these kind of weights, if you have a 5 for the doctor feature and a -2 for the professor doctor, this would lead to the exact same prediction as if you had a -1 for the doctor and a 4 for the professor doctor. Yeah? Why is it so? Because you can imagine you have this sum, yeah, and basically you always multiply this with the same value as this. So you could do the same thing and just take the sum of these and multiply it with one value. And you see that the sum is the same. Here 5 minus 2 is 3, and minus 1 plus 4 it's also 3. So basically always when the sum is the same and they would be like a duplicate feature, this would lead to the same predictions. And that's why if you do look at the weights to see what it has learned, you have to look at the weights a bit together. Now there's one thing, in practice there are certain methods called regularization, where you try to keep all of the weights as small as possible. So then you would hopefully get here just 1.5 and 1.5. And then this problem is, yeah, you have less of this problem because all the weights are kept small and they should not get these kind of weird values. But still, you should know that. And also, another thing is, if your features are in a different range, let's say you have 0, 1 features, like we just mostly had 0, 1 features, word is capital or not. But you could also have a feature like the length of the word, and that may be between 1 and 100 or something. Then the weights are affected by how big or how small your feature value range is. So if it's very big, for example, automatically your weights should get smaller, yeah, because you multiply them, and in the end you should, for example, if you have 2 features that are of equal importance, but one has a much bigger range, then this weight will be smaller, because this should come out the same. And what you usually do is also you can just scale the features so that they are all in the same range. Yeah. Yeah.
In this example you gave us, would it not imply that both features have the same value for every observation, that you have a multicollinearity problem?
Huh?
A multicollinearity problem with your design metrics?
With what metrics?
Well, when one column is a linear combination of other columns, in this case they are the same. I think it's not even possible to use the algorithms for regression with metrics like that. Okay,
actually I don't know that. Like, I just know that, yeah, if you have strongly correlated features, then you have this problem. I don't know if you cannot use them at all. Maybe, I'm not sure.
Well, I think you can, but the estimations you get will be
really wrong.
Yes.
What you mean? Okay. Even if you use regularization, or is it good?
Good question. It has to do with the numerical aspects of the position number of member. I don't remember exactly.
Okay. To be honest, I don't know that. Like if it would not work at all. But yeah, at least I know that if they are not perfect, in our case they are perfectly correlated. If they are just strongly correlated, then the algorithm should work, and it should be less affected than naive Bayes by this strong correlations. So you can be a bit less careful about your features. You can have correlated features. Yeah, now in general, like a comparison about these two. In general, logistic regression is better with more data, and naive Bayes is better with less data. What does it mean? It means that naive Bayes reaches its optimum with less training examples. So it reaches its optimal classification a bit faster, but logistic regression has a better optimal classification. So I'll show you some graphics, some diagrams. What you see here, this dotted line is for the logistic regression, and this line is for naive Bayes. So you see that, and this is the amount of training examples here, and this is the error. So you see here the error for naive Bayes. It goes down very, very quick, yeah. But then it stops around this thing here, and it seems to converge somewhere around here. And the logistic regression goes down slower, but it converges to a lower value. So the error of logistic regression with enough training examples will be low. And yeah, this has basically been shown also mathematically why this is so, that naive Bayes needs less training examples to reach its optimum. But yeah, that's just something you should know. For example, if you have very little training examples, for example here, then naive Bayes might actually be the better choice, because logistic regression will not be able to reach its optimum with very small numbers.
Does this not depend on the problem? Whether it's like this or like that? So these figures are for which problem?
These figures are for different kind of problems. So they took, like, in this paper what they did, they took very famous data sets and they used them and they showed it. I mean, I think that no, it does not depend on the problem, because there is mathematical reasons for it. It's not just that they determined it empirically, that you have this graphs, but they are they showed that mathematically, I think the naive Bayes reaches its optimum in logarithmic order of the training examples, or logarithmic order of the features or something, and logistic regression in a linear relation to the number of features. So there is not it's not dependent on the problem, I would say. I mean, of course, in practice maybe there will be differences, but it's a general characteristic.
But they are also incomparable in one sense, right? For logistic regression, you need numerical features. So if you have non-numerical features like part of speech tag,
Yeah.
then you have to map them in such a way that higher values mean more this and lower values mean more this. But this doesn't always make sense, right? If you have 5 discrete values.
Yeah. If you have 5 discrete.
Or, I don't know.
But you can always make a mapping. Like if you have 5, you say you have 5 categories, yeah? Then you can make one feature for each, just 0, 1, 0, 1, 0, 1, 0, 1, 0, 1.
Then you increase the feature space.
Okay.
And then you learn slower.
Yeah. Okay. Yeah, I don't know how they counted exactly the features if you have this kind of problem.
No,
but
what
yeah.
I mean.
Yeah. You mean something else? Yeah.
No, just take part of speech tag.
Yeah.
And this will just appear in your logistic regression as a numerical feature, and then you multiply it by some weight.
Yes.
You have to turn it into a number.
Yes.
So you are saying you can always map it in a numerical range so that what you're saying, you order them or what? That's what you do.
Huh?
You want to order them, the categories, the part of speech tags, and then give them numbers 0, 1, 2.
Yeah, I take them as individual features, the categories. Yeah, that's what I would do.
Oh, that's what you're saying.
Yeah. Each one has an individual feature. Now what he said, okay, I didn't think about what he said, that automatically increases your amount of features. But yeah, that's what you can do. So yeah, I mean, I will put in the slides, I didn't put it yet, but I will put in the slides later the link to this paper. And basically there it's all written. Like they show it also mathematically, like how you transform it and why is also mathematically provable that this one will reach its optimum faster by naive Bayes and the other one not. Yeah. So it's, yeah. Okay. Oh, sorry. Now I will show you one more algorithm which is very popular and which tries to solve similar problems like the ones before, and it's the support vector machine. And what the idea of the support vector machine is, you try to separate like true and false examples or examples from different categories by a big boundary. So what does it mean? Let's say here we count the animal and plant words in a sentence, yeah, and we count the sports references. And if you have many sports references, it's probably Tiger Woods, and if you have many animal and plant words, it's probably just the animal, not Tiger Woods. And now we could get some graph like this, yeah, with here are these animal, and here is Tiger Woods. Now what SVM will do is it tries to draw.
What's each dot now? I'm confused.
These dots
so
is
now what?
These dots is occurrences of the word tiger when it is meant as an animal. Yeah. So you have tiger somewhere appearing, somewhere here appeared tiger, and in this sentence there were, yeah, it's not a very realistic example. Okay, there are 5 sports references and 3 animal and plant words, and it was actually an animal.
So each marker is a sentence.
Each marker is a occurrence of a word. Is a word, but I mean each word occurs inside a sentence. No, so you could construct. Yeah. Yeah, I think, how to say, to show what the SVM does in a 2D plot, it's good to have some numerical features. That's why we tried to come up with some numerical example with numerical features. And yeah, so this here means I have just 2 sports references, but 4 animal words, and then it's an animal. And here I have in the same, yeah, sorry, let me see. Here I have a different word.
Each marker is one word occurrence, sorry.
It's the classification of tiger in that sentence.
Yeah.
So we examine features of the sentence.
No, the things, the colored things are
okay.
objects, right?
Let's say.
So it's objects. And
yeah.
we have 2 values. Each object has 2 values.
Yes,
so
because
what is each object?
Each object is a word. Let's say we have 1, 2, 3, 4, 5, 6, 7, about 10 words, and they all are in different sentences. In this example, they all occur in different sentences. So we take as a feature, for this word, we just remember for this word occurrence how many animal and plant words are in the same sentence, just where it is. And here we take, okay, how many spots, or we always take both animal and plant words and the sport references.
Okay.
Yeah, we had to come up a bit with a...
That's confusing,
yeah. Yeah, it was not so easy to find a numerical example for our named entity recognition. So yeah, but this is just one word, and we pretend they all occur in different sentences, so we can always look at how many sports references are in the same sentence, how many animal examples. Okay, and now, okay, what does the SVM do? It tries to make this line, and it tries to make this line in a way that there is a big boundary between the closest positive example and the closest negative example. So it tries to make this margin as big as possible. And that's basically already the main idea of the SVM. And yeah, now about training, or about training, it's, again, I will not go into detail how it exactly is being done, but there exist a lot of algorithms to do that very fast. But there's one more aspect. Usually your data will probably not be separatable like this. Like there may be a triangle here somewhere, or a dot here somewhere, or just here. Yeah. Now you have to do something about that, and what you do is you do this soft margin technique, and this allows for some wrong classifications. You get some parameter for your SVM, and it will make a trade-off between two things. First of all, for the SVM, the data points should be on the correct side of the boundary, and they should even be outside of this margin, yeah, because otherwise margin gets smaller. But also the margin should be big, and basically your parameter tells you how important is this and how important is this part. And then you can use this SVM even though they are not perfectly separable. And as I said, yes, there are specialized optimization algorithms to train the SVM. Yeah, I think that I just want you to know this basic idea here. You have this line, and you try to really separate this as good as you can by really making this boundary as big as it can be. And yeah, if you have more dimensions, it will not be a line, but it will be a hyperplane. Yeah, if you have a lot of dimensions, with 3 dimensions would be plane, and then 4, 5, 6, and so on will be some hyperplane that tries to have a big margin to the closest positive and closest negative example. And they're used often very successfully. They're quite popular. They're quite robust and fast. One reason for this is that you can see that this point actually here, also this point, this point here, it doesn't really affect the classification, yeah, because only these so-called support vectors, that are the vectors that are actually on the boundary, directly affect the classification. So let's say we had the same set, but this point was missing, the classification would be the same. Yeah? So that makes it yeah, a bit robust against missing data. And yeah, but what you have to know, they're very popular, very used. Yeah. Now about the interpretation. The interpretation maybe is a bit less obvious, but it's still possible to see what feature matters how much, like is a feature important or not. If you look at, sorry, if you look at this margin here, yeah, or if you look at just at the slope of the line, it seems pretty obvious that the important part is the sport references, yeah, because if you have a lot of sport references, it matters more than these animal things, yeah, I mean, because the line is almost like this. If it was like this, then only the sport references would matter. So what you could look at is, if you look at this thing here, this boundary, if you look at some vector here and you project it down, how big is it? Here it would be bigger on this, and it would be a bit yeah, smaller on this, like maybe just like this. Then you can get some idea which feature matters more. So it's a bit more involved, but yeah, you can still get some idea what your SVM actually learned. Yeah. Okay. Now, one algorithm which is a bit different, because before they are all pretty similar. They try to make this classification, and they're pretty similar, and they make this linear boundary and so on. Now, something that's different is decision trees. And what they try is they try to recursively separate the data by finding the features that split well into yes or no, or into the different classes. So one example, we could have the first feature is word, because a word like Michael is maybe always a name. Yeah, so then we're already done. Or we could have a word like tiger, and then we could use again our sports references in the same sentence. If it's less than 2, it's not a name. If it's more or equal than 2, it's a name. Yeah, let's say it was like that. Or we could have something like Spears, which may be like the Spears you throw, or it may be Britney Spears or some other person called Spears. And you can say, okay, you're not sure. And then you just say, okay, if it's not written with a capital letter, it's certainly not a name. But if it's written with a capital letter, then there's some 90% chance that's a name, for example. And how do you do this? You start by having all your training examples here. So all your training examples are here at the root node of the tree. You don't have these lower levels yet, you just start with some root node. Now, you pick some feature to split the training examples into the next subtrees. So here you have your next subtree, and here it's already a leaf. And how do you do it? You pick a feature so that these training examples are mostly from one class in the subtree below. Yeah. So, for example, here we only have names, so we can already say this should be a name. And here maybe it's mostly maybe for the tiger it's mostly names and just a few not names, and then it's also a good way to split this. Because for example, if you take some random feature, as a counterexample, what would not be good would be taking some random feature, like let's say the number of a certain character, let's say the number of ends or something, Then when you split into the subtrees, you will get a very similar distribution of names and not names as in the root node, and you will not get very close to classification. So you pick a feature so that the training examples one subtree are mostly from one class, and you just repeat this procedure on all the subtrees again and again, and you always split into the subtrees. You're finished when one subtree only contains examples from one class. Then you convert it to a leaf. If there are only person names left after you split and split and split, then you can say, okay, if I arrive at this leaf, like here it's already at the start, if I arrive at this leaf, oh, it should be a name, or here, it should be a name. There's one more thing. Usually, I kind of put it into the example as well. Usually, you will probably not be able to split it so well that you always arrive just at one class. And then you use some threshold, like let's say if 90% are names, then I just stop. And then you can also decide whether you will classify this always as name or whether you will give some kind of estimate, okay, 90% chance is the name. But this basically just split, always down until you can't split anymore. It's useful especially if you assume some feature interactions. So if you have something like this, when it's tiger, it could be a name, but if there are less sports references, then it's not. If you have these kind of interactions between the features, then it can be quite useful. And also if you have some non-linear relationship, if it's not like it goes up, then it's a name, it goes down, then it's not a name. For example, let's say, I actually looked this up, most of the names are in some range between 3 and 10 in the English language. So if it's shorter than 3, probably it's not a name. It may be something like this kind of words, probably not a name. If it's between 3 and 10 characters, it might be a name. And if it's more than 10 characters, it's unlikely to be a name. And this you can also directly use in your decision tree. You could not just say less than 2 and bigger than 2, you could make less than 2, between 2 and 10, and bigger than 10. So for this kind of relations from your input to your output, it's also useful. And in practice, often you don't use one single tree, but you use many trees which maybe recognize different kinds of person names. For example, Spanish names and English names, or names, names from sports persons, names from politicians, and then you somehow combine all their classifications to get an idea, is it a name or is it not? And to interpret the learning of a single tree, it's very clear, like you just basically look at it, you can see, okay, this is what it learned, and you can think, oh, does it make sense, does it not make sense? And for these forests, like forests mean you have these many trees, there are also methods to see how important is one feature over another,
If you're using many trees at the same time, won't you be making the same comparisons multiple times and wasting time doing that?
No, because what you do in these, or at least one of the ways what you do, is that you introduce some randomness in your training data. You will change them, you will randomly change some training data, for example, by permuting some features around, so that you actually have some noise in your training data, and you will make different noise for the different for different trees, and then you will get different kinds of trees in the end, because maybe there was some noise, so it could not, there was one feature it could not use because of the noise, but the others it could use, so it will focus on one specific part of the features, one tree, and another one on another. And there this one technique, there are also other techniques where you explicitly say, okay, I change a bit the order of the feature. For example, what you could do is You say, okay, I always take this feature which is best, but every some random times I take a random feature. And so you automatically get different trees. And that's why you're not always making like exactly the same comparisons. I mean, yeah. That's how you make sure that you don't, for example, otherwise you would always get the same tree. No? When you always start the same and you make exactly the same kind of computation, you get exactly the same tree. So you introduce some randomness, that would be one method, random forest, that you get different trees. And you can introduce randomness at different levels. You can say at this point of the algorithm, I just pick one feature randomly, or you can induce some randomness in your training data.
But even if there are different trees, that any feature that's being compared in both would be a comparison that's the same, right? For a given value.
No, because I'm not sure what you exactly mean, but you can imagine that if you're down at some subtree, you will have different training examples already, because you split differently before. Yeah, so you will not have the same training examples. Of course, if you start at the top, you have the same, but already, like if you start differently, you will have different training examples for the different subtrees. So you will not have the same training examples in the subtrees. Yeah, and also, as I said, when you make some noise in the training data, then even if you have the same training examples, you get different results because they don't have the same values anymore. So what you could do, for example, what is done is you take one feature and you just change all the values. You just, like, for example, you commute them around. Yeah, so that if before training example 1 had, I don't know, it was capital, now in training example 2 it was not capital, you change them. Yeah. So what this makes is that your tree can no longer rely on this feature because it's pretty random, and then you also get different results from the splitting. Yeah. Okay. Okay. Now our last algorithm. And now if you compare the two sentences, Tiger Woods played golf and Tiger ran into the woods. We still have the same question. We always have this. Where is it a name and where is it not a name? And now there's a helpful characteristic of the sentence we did not use to find out which one is a name. Can you guess which characteristic did we not use to say this here is a name and this is not? Color of highlighting was not considered. But actually, yeah, if you look at the color, it's already a hint.
The verb.
Huh?
The verb.
The verb.
Yeah. Tiger Woods can play golf, plays, but
yeah.
Tigers run.
That would be an option. That's not the one I meant. That would be an option. But
they are next to each other?
Exactly. They are next to each other. What do you mean with that?
I don't know.
You don't know. Yeah, but they are next to each other. And if you think about it, normally names, if you spell them out, there are two names next to each other. No? Like my name, Robin Schirmeister, or Hannah Bast, or Tiger Woods. Yeah, there are two that are next to each other. So if you have two words next to each other, and for both you say it's fairly likely that they are a name, then it's very likely that they are a name because they are next to each other. If you say individually this is likely to be a name and individually this is also likely to be a name, this word, then because they're next to each other, now it's very likely that they are a name. And so far we haven't used this at all because we have never used the classification. Yeah, that's also that. Tiger and Woods could both be names, and two parts of a name standing together are more likely than just one part. So if you just have the tiger and you say, oh, it could be a name, it's less likely than both.
But you could also make that a feature, right? And use one of the previous approaches.
You could not make that a feature because
you could first run the whole thing, and then you could make it a feature. Is my neighboring word?
Okay, then you have to run it twice, basically. That's what you're saying.
Mm-hmm.
Okay, yeah, I don't know. I mean, then it would be like a different algorithm, I guess, if you run it twice. I don't know.
Also, there's n squared more features as a function of your length of sentence.
Why?
Because you have to have every word with every possible neighbor of n away. Tiger is 2 away from playing.
No, the feature is just my neighbor was tagged as. It's just one feature.
Yeah, I mean, if you run it several times, of course, I don't know what you can do. I mean, you can always modify this algorithm and then they become more similar. But if you just run it once, like if you just run SVM once or something, then you cannot use this as a feature, basically, if you use a basic algorithm. Okay, so the conditional random fields ideas that you use the surrounding classifications and the surrounding data points. Now, surrounding data points you could already use in the something before, but now we also use the surrounding classification. So you use the fact that names often stand together, for example. And this is kind of a different model. So before we had always like a single input to a single output, like one word to person or not person. Now, what these conditional random fields idea is that you say, okay, it's actually, naturally it's a sequence. A sentence is not it's not isolated words, but it's a sequence. And so also it will take a sequential input and it will give a sequential output. Yeah? So these labels will also be seen as a sequence now, and they will not be just treated individually. And for us, you will now only use the neighboring classifications. In the general conditional random fields, you could also use like a classification, I don't know, 5 words ahead. What is the class? But you will only use the neighboring classifications. It's called linear chain conditional random fields. And yes, from Sketch, I hope you will get this. So, what do? We use feature functions to get some probability for a class sequence. And what are these feature functions? So these feature functions, they get the class label from the word before, and they get the class label that your algorithm is guessing for this now, or it's trying out all the class labels now. So it will also get the class label for the current word. That's the one that we're trying to classify now. And it will have access to all the words of the sentence. Yeah, it will just get all of these. And then each individual feature function, which you have to define by hand, which will give out some real value. Maybe, again, just 0, 1 function, which just gives out 0, 1. That's very typical. But it can, in theory, give any kind of real value. Now, you can have a lot of feature functions, which look at names standing together, a verb after, or what kind of verb is, because we had that. And then you add all of the values of these feature functions, and you get some kind of score for the value of this class 2. Yeah? And that's now if you have another point here, then you just do the same again and you add this value again. So you have some big sum, and in the end you will get some kind of estimate of how likely is this sequence of labels. And I already said these feature functions, they can use the complete sentence, the current position in the sentence, the class of the output node before, and the class of the current output node. That's the one that you will likely put in all the different possibilities and see what is the highest score. They will return some real value, and now each feature function will also be multiplied by weight, and this is what needs to be learned, because the feature functions you will define them by hand, as I said, but then these weights is what you will need to learn. So let's look at some examples which illustrate what could these feature functions be. Washington Post wrote about Mark Post. Now we see that this is a newspaper and this is probably a person, and in general the rule may be if we had classified this. Let's say we also have a label for a city, yeah, not just person, not person, also city. So if we have a city plus the word post, then it's a newspaper, for example, so it's an organization newspaper. And similarly, if you have a thing that was a word that was classified as a name or first name, and then we have post, then it's probably a name. So this would be an example of a feature function. Another thing may be Dr. Woods met his client, and we can say we classified this as a so-called salutation, like Mr. Doctor. And then it should be usually followed by a name. So this could be another feature function that we say if there is a salutation before, give it 1, and if it's not, then 0, and then you can learn that this should be a name. A feature function does not have to use all the inputs. So it can just look at what we did before. It can look just if the word is capitalized without looking at any classes around it, and can look what is the part of speech of the next word, for example, is it a verb or noun or whatever. It can just look at the part of the inputs. Now, how do you use this? You define your feature functions. That's what you have to do again. You have to do it by hand to define your feature functions. Then you use an algorithm to learn these weights, and then you classify. The classification now, it seems a bit more complicated because I told you that here we just had the score for the one class. Yeah. Now we will make another score for the next class using whatever we classified this as. But in the end, in theory, we need values for all kinds of combinations. So here person or not person, and here person, so person, not person, 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 not person, not person. We need all these scores because we want to classify the entire sequence or make some estimate of the entire sequence. Is the sequence likely or not? Now for general conditional random fields, that's really complicated, but because we only use we only always use the output node before, we can actually just like run through it using dynamic programming. So we can just always remember, okay, all the possibilities here and all the possibilities there, and then we get a lot of values. And then we go one step further, and we can just go on, and we can kind of forget this here, because this here will no longer affect the number 3. Yeah. So this is why it's possible to classify in polynomial time without having to go through all possible sequences, because we only depend on the node before. Yeah, this is used a lot, like named entity recognition, or if you make part of speech in some noisy text, because if you have very well-formed text, actually you might be okay without using machine learning even. You can just use some rules. Okay, this was the last algorithm. We'll just now talk about some characteristics, what differences between them. First, they all make different assumptions on the data, so you have some linear relationship.
Another question?
Yeah.
It's the same question again. So if you just...
Same question, okay.
Yeah, sorry.
Yeah, that's fine.
So if you just use the neighbors to classify,
Mm-hmm.
then you can, or let's assume you just use the right neighbor. Then I just double my features. So I just take the feature for this word, and then I take the feature for the neighboring word. So I have twice as many features, and then I use one of the classifiers before. Then this thing can also learn what it wants from the features of my right neighbor and also of my left neighbor. So by just doubling or tripling the number of features, I can incorporate information about my neighbor. Right?
I mean, you could.
So I wonder what's the difference then to conditional random fields. So you could do it that way, right? But then
I'm not so sure whether you get the same result. I'm not sure how to see
so if you go back
Yeah.
a few slides to the picture,
Yeah.
I think it's similar to hidden Markov models. And what you want in the end is the sequence that maximizes the score.
Yeah.
And so the decision for class 2 depends on what you say class 1 is classified as.
Yeah, but if you take them as separate features.
But you want to take just the input values as separate features. Like you want to take the word before and all its features without the classification as features for word 1.
Exactly, so I have a word, I want to classify something, I take all the features of this word, like you explained, capitalization, part of speech tag, and I also take
But I don't know
the
if you
features of
really-
the neighboring
yeah.
word and the word to the left.
I don't know if
Now
you.
my whole
Yeah.
thing learns something, no?
Yeah.
I mean, it can also learn what it
But
wants.
I'm not sure if you really get all the combinations and their effects. Like, I mean, you have let's say 5 classes, and you could have A, B, and C, B, and so on. And I don't know if you just take all the input features, if you get the same result as if you really take the different possible classifications. I'm not sure
So
that you really get that.
in this example, right, it can be that you have to choose a class for class 1 that has a small probability.
Yes.
Although there may be another classification that is more likely.
Yes.
Because then you, in the end, can choose something for class 2 that is much more likely, and in the end you get a higher score for the sentence.
Yes. Yes.
And that's why you need to use Viterbi for determining the maximum, the optimal sequence.
Yeah. So yeah, it can happen that you take not the most likely one for class 1, but you take a less likely one, because in combination with this one, the overall sum will be higher. I mean, that's basically it. That's why you need, I mean, I don't know, let's say, no,
Yeah, but that's what every learning algorithm does, right? You have your training set, and some things in the training set are not so great. And it will assign the probabilities. You have a training set,
Yeah.
and now you compute your probabilities,
Yeah.
and now you can apply, you can classify the things on the training set, and they will not all be classified correctly, right? Some of them might be classified totally wrong way. I mean, this is just...
But that's not, I don't think that's what I mean, because what I mean is, you actually classify correctly. So you have like a sequence of words, and you classify them correctly. It's just that you have the first word of the sentence, you have to give it a class that seems very unlikely if you just consider this word. Because in combination with the next classes, the sum is high. Yeah. Yeah. So I don't know if you get this if you just double the input features.
So what I don't get is what is the difference to a hidden Markov model then?
Difference to hidden Markov model?
Yeah.
As far as I read about it, basically it's a similar difference between logistic regression and naive Bayes. Because hidden Markov models, what it tries to estimate, or let me, I don't know where it was. I mean, that's why I also wrote this thing here, blah blah blah. There to come. Yeah, see? So, I mean, what the naive Bayes actually does, it makes this intermediate step of computing the chance that any word is the word tiger and it's a name. So it's that's why it's called a generative model, because it tries to first compute this chance that both occur, that this input and this class occurs, basically, and then you can do this normalization to get the conditional probability. And as far as I understand, the hidden Markov model does the same thing. It first looks what's the chance of this sequence and this output sequence, this input sequence and this output sequence. And the conditional random field, I guess that's why it's called conditional, it estimates this conditional probability that given this input, what is the most likely output sequence. It computes this directly. Yeah. And that is the difference. And
yeah, but I don't. Is it a technical thing that you can use now? That you can suddenly use numerical features instead of categorical features, or
is it a technical thing that you?
Yeah. Or what is the reason? In one case you have a conditional probability. In the other case you have a joint probability.
Yes.
And so why is it that now you can suddenly use so many and different numerical features so easily?
So many.
You know what I mean? Because
yes, kind of. Yeah. I mean, I'm not sure if this is if this will answer your question, but no, I'm not sure. I think that the conditional random fields, it has less constraints than this Markov model. Yeah. So for this hidden Markov model, you always have these like this probability. So it has to be between 0 and 1. Yeah. You have this the probability going from one state to the next. It is between 0 and 1, and has to add up to 1 also. And this, I don't know what it's called, this probability that this hidden state emits this observed state. Yeah. Also, again, it has to sum up to 1, and it's between 0 and 1 and so on. And yeah, you just don't have these kind of constraints. And I guess you don't have these kind of constraints because you don't try to estimate the joint probability first, but you try to estimate the conditional probability directly. So if you, again, I didn't put this here because it's more complicated. It's a bit more involved. If you in the end, if you want some probability, you have a normalization step as well for this. So you have to use some normalization step, but it's a bit more complicated how you do it. Yeah, because theoretically you have to have the possibility, the probabilities of all the sequences and divide by it, but that's not possible. And yeah, so it's a bit more complicated. But yeah, I think the reason really is that you don't try to, you don't have this intermediate step of computing the joint probability. And that's why you have more freedom in how you, in what your feature functions can do and stuff. Yeah. Okay. Sorry. Okay, we're not far. Yeah, so these are algorithm characteristics. I already said the assumption on the data, maybe true or not. Then how interpretable is it? Was it learned? And there's the computational time and space. I didn't really go too much into detail of that, but of course some are faster, like naive Bayes, some are a bit slower. There are different types. They can handle different types of input, categorical, numerical. Although this often it can be transformed from one into the other. Yeah, but a more important difference, of course, if they handle single data points or if they handle sequences like conditional random fields. Yeah, now one more thing about types of machine learning. So far, we looked at supervised learning. So supervised means we had pre-classified, we had this training data that we could learn on. And unsupervised algorithm means we don't have pre-classified training data. And this might happen, for example, if we want to know what kind of topics are right now on the news sites, and we don't have training data yet, what is annotated in. Then what we can do is we can work by clustering. So you could say similar data gets the same class. So we have two news reports that have similar words. Maybe they refer to the same topic, and if they use very different words, they refer maybe to different topics. And this is how we can cluster them. Then we still don't know what is the class, but we know, okay, these are one class, these are one class, and so on. And one thing that's important for, I think, your papers and for a lot of NLP is like variants of that, so semi-supervised stuff. That means you try to create more training data automatically. So you already know that if you have a big amount of training data, it's important for good classification. But creating training data by hand is time demanding or sometimes maybe not possible. And your unsupervised algorithm, it already gives you data points with classes. So even though you don't know what these classes mean, you have class 1, class 2, class 3. What you could do, for example, you could just use these then with a supervised learning algorithm. You could look at these classes, maybe even give them labels because you understand what they mean. I don't know, maybe the topic is, I don't know, something from the news, some news topic, and then you could use this for your supervised learning algorithm. And there are also other ways, like you could use just some very simple rules to give you training data. For example, doctor is almost always followed by a name. So you can just say, okay, I take all the words that follow doctor in a big corpus of text and say these are all names, and then I use these as training data. Yeah? So this would be giving you more training data automatically. Another thing is if you have some classifier already, and it gives you some idea about how confident it is. Like logistic regression, it says, I have this word, 99%, it's a person. Then you could say, okay, I use this thing which is classified with very high confidence, again, as training data. Now, this is a bit dangerous, of course, because if you have some systematic error, then you will also get erroneous training data. So you have to be careful. Yeah, but I think it's very used in natural language processing because often you have a lot of text, but you don't have a lot of annotated text or a lot of pre-classified text. And now what can you do to improve some machine learning system? First, it's important to know if and how you can actually improve it. Maybe in your overall system there are bigger sources of error than your machine learning system. Maybe your annotations are incorrect or very incorrect, like your training data or other things are not working well within your system that are outside the machine learning algorithm. Or maybe like your current data, it's just not possible to learn more than your algorithm actually does. It's just not in the data. Yeah, what can you do in general? Like if you do believe, okay, my machine learning is really not classifying well and could do much better, you can try to get more data. You could try to use different features. You could pre-process more, like also clean your data more. If you have some very weird data that's just wrong, like you have a lot of text and some actually is not text, but I don't know, you have some website and you accidentally have some HTML text inside and you find this and you can clean the data, or you could use more different features. Or another thing, of course, you can also just try to use another algorithm. If you think my data is good and the information is in there, the features are also good, then you could use different algorithms or combine different algorithms, to get some better classification. Machine learning in natural language processing, it's fairly widely used. I think like 20, 30 years ago, I don't know, it was not so much used, and then it started to be used more and more. And I think it's two reasons that I think why it's used. It makes it easier to create systems that deal with a new or like noisy text. One example was these tweets. I showed you a tweet. People don't write like grammatically correct there all the time, or they invent new words there or whatever. And also one example I saw was like free text on medical records. So if some doctor, for example, he just wrote something down, some diagnosis quick, and then they try to put it into some recording system, then it's not grammatically correct and it's very chaotic. And there you can't maybe just use handwritten rules. You have to learn a little bit where is the diagnosis, where is the medication, and so on. And it can just be easier to just specify the features and learn the classification rules automatically than write all the rules by hand. So this was it. Now let me make a summary. So the typical machine learning, it consists of the data acquisition, feature design, algorithm training, and performance evaluation. Many algorithms exist with different assumptions on the data. It's important to know whether your assumptions match your data. And it's also important that you always know what is actually my overall system goal. If I use my machine learning component in my big goal of finding all the names and whatever, what's my overall goal and what should my machine learning algorithm actually try to optimize? Yeah? Okay, that was it.